move on now to something totally different. Petrônio Cândido, the Silva, who will talk about some hands-on concrete work with some practical agent-based simulations of COVID-19 spreading. So Petronio is a professor of computer science and computational intelligence. He's at UFMG in Brazil, and I was very pleased to discover Petronio's work on agent-based modeling of COVID when I started looking in depth into this a couple months ago, and I was also pleased to see he's from Minas Gerais. I mean, I'm dual citizen, American Brazilian. I was born in Brazil, but I was born in Rio. But actually SingularityNET's AI office is in Minas Gerais, although in Belo Horizonte, not in Monte Claros, where Petronio is. So I'm happy to see some more AI brilliance out of Minas Gerais. And yeah, Petronio has done work in a variety of areas of computer science, but one of them is agent-based modeling, and he's put together a simple but very well structured agent-based model of COVID-19 spread. And as I'll talk about later today, we've taken his model and even extended it a bit in some of our prototyping in SingularityNET. And Petronio also has put up an outstanding blog post on toward data science, where kind of goes step by step through the very basics of what is agent-based modeling, how does it work in the context of COVID-19 in particular. So I mean, we're not seeing like super intelligent agents here, and we're not yet seeing a very large scale hyper realistic simulation, but we're seeing the core elements of what agent-based simulation is, which is a very valuable practical thing to understand. So if you're a developer who have even a little development skill and want to get your feet wet playing with agent-based modeling in a COVID context, I mean, Petronio's blog post and the code he's made available are an amazing place to start. So yeah, take it away, Petronio.
Okay, well guys, I'm going to, first of all, thanks for inviting me for this presentation today. It's I'm very pleased to be, I'm very honored to be invited, and I will share with you a presentation. Are you seeing my desktop presentation?
We see a giant QR code, yes.
Yeah.
Okay.
So if you want to open the slides in your computer, you can use the QR code or this URL, right? Well, today we're going to talk about agent-based simulation of COVID-19 health and economical effects, right? We're going to talk a little bit, give a small introduction. I have to apologize with you because I put some very introductory material here because I myself invited some people that don't have the simulation framework, don't know this simulation framework. So I will give an ultra fast introduction. Then I will talk about agent-based modeling, about the package we developed, the COVID ABS, discuss some initial results, discuss some work we're going to develop after this first step, that the step of the simulation, and finally the conclusions, right? So let me introduce myself. My name is Petrônio Cândido Silva. Don't worry about the pronounce. My name is hard to pronounce even for Brazilians. And I'm a professor, researcher, and developer live here in Brazil, right? Well, why we are here? We are here basically because the initial responses to COVID-19 were a disaster, okay? There's a lot of people doing forecasting, doing trying to forecast the number of infected people and the deaf people, and they don't thinking in other aspects of the pandemics, okay? So we can do a lot of more things, okay? We can start helping the governments to improve their disaster response and management to COVID-19, right? So the framework I will propose today, it's based in first forecasting using agent-based simulations, dynamic robust optimization, and decision making. So we're gonna discuss all of these aspects in the certain time. Okay, let me give a small and ultra fast introduction to the simulation. So let's start with the known effects of the COVID-19 pandemic. Well, there are very concerning effects. There are other not too concerning effects. Of course, the more concerning effects are related with the healthcare system. Okay, the number of hospitalizations, the number of deaths. This is the most concerning effects. But how about the other effects? Here in Brazil, we experienced huge an explosion of the cases of domestic violence. Okay, the cause is obviously the quarantine. Okay, on the other hand, we are observing a dramatic diminution of the number of traffic accidents. Okay, and also an explosion of psychological disorders. We never can forget the tragedy of the economics, the number of the unemployments, the explosion of public spendings, and there also other less concerning aspects like the environmental ones, like the reduction of the carbon emissions and the increase of the solid waste, domestic solid waste. Okay, so why we are here? We want to give an holistic view of the pandemics, considering not only these healthcare system problems, but a little bit of all of these problems. But we're going to focus in second place in the economical problems. Well, once we talked about the effects, let's talk about the causes. We know the primary cause is COVID-19, of course. But what are the secondary causes? For example, the environmental causes that were discussed, the temperature, the humidity are affecting the rate of contagions. The effects are very impacted by the political misconceptions and wrong decisions of the rulers, some social habits and misconducts, some in the economic aspect, the poverty can be considered a secondary cause, and well, a lot of causes besides the COVID-19. Well, what are we gonna do? We're gonna create a model that mimics the pandemics, okay? The pandemic. We want to base it on the data sets, on the knowledge base we have about the COVID-19 disease. We want to create a model that mimics all these behaviors. So we check the simulation results, compare them with the data sets, adjust the parameters, and create new models that become more and more accurate and better replicate the pandemic behavior. So as we got more accurate models, we can test interventions that will be applied to the real process or the population under the pandemic. Okay, so our model, it has input parameters that we called by the Greek letter theta. It has an internal state we call S, and we have a set of response variables we call R. Okay, so the model is a function that accepts the actual state and the parameters and generates a new state, internal state. This change for the actual state, the current state, for the new state are stochastic change that depends on the current state and the set of the parameters. Okay, so given a little bit more of formality, we can discuss the simulation framework as the initialization of the internal state. Okay, this initialization is affected by the set of the parameters. The parameter set is composed by a set of constants and a set of decision variables that are the variables that we can change. Okay, and the main loop of the simulation is the continuous updating of its internal state. Okay, the time evolution of its internal state given the set of the parameters. And the response variables are some kind of summarization or aggregation of this internal state. Okay, well, what is our general goal with this model? The first general goal is to help the government. How to help the government? Prescribing interventions. What is an intervention? It's to change a decision variable to achieve a desired level in the response variable. Okay, but there's a problem in that. We have no data for everything. There are many effects and causes that are not jointly sampled. Okay, it's simple to give an example. If we want to control the environmental effects like the carbon emissions and the solid waste, this is not being recorded together with the statistics of the pandemics. So it's hard to train a model that correlate these two variables. Okay. So we have a possible solution that is create hypothesis. Each hypothesis is to, given a change in a decision variable, what will be the response on the response variables? What will be the change in the response variables? Okay, create scenarios inducing all possible cause and effect relationships, and simulate all scenarios with all conditions, and aggregate data and improve the models. And this is a continual cycle of data-driven and optimization tasks. Okay, so what is the agent-based simulation? Hereafter we call it ABS. Okay, the agent-based simulation, we start with the model-based simulation. The worldwide famous susceptible, infected, recovered model. It's a system of differential equations. Okay, and this is the most used model, the simulation model currently. Okay, it has some variations. The SEIR, susceptible, exposed, infected, recovered model. There are some new extensions like the SIRX, where X means the symptomatic quarantined cases. So there are a lot of people using this model-based simulations, and there's a why. Because they are simple to implement and computationally cheap. But the problem with the model-based is the limited number of effects being measured. So we have 3 effects being measured in the first model, 4 effects being modeled in the second model, the SEIR model, and 4 effects being modeled in the last model. So if you want to simulate more things, to consider more things than these 3 states. So for this, we have to use agent-based simulations. The agent-based simulations we used to simulate complex dynamic systems that are composed by discrete units. We call it agents, and these agents interact with themselves along the time. Okay, the global state of the system is an aggregation of the individual states of the agents. For simplicity, we're going to make the assumption that the time is discrete in all our simulations hereafter. Well, let's synthesize. Each agent of my simulation have its individual parameters, and actions have its individual internal state. There's also a common environment that is shared among all agents. This common environment has shared parameters and also actions. And this environment interacts also with the agents. Finally, there's a population of agents living in this common environment, this shared environment, and inside this environment, the agents interact between them. Is when occurs the contact and maybe the infection. Finally, the response variables generally are statistics about the aggregate states of the population, internal states of the population, okay? So let's suppose this simple scenario here. So we are in the first iteration of our simulation. We have a set of the theta set of parameters as input, and the current state is that each one of these circles are the agents, the color of the circles are the state of the agent, and we have the output response variables are in time t, right? So I start with this red circle, and it's characteristic that this red circle, this agent, is close to another 3 agents, right? So this great circles is the radius of contact. All agents that are inside or crossing this radius are in contact with this red agent, okay? So they are sharing information, they are interacting. So the agent within the red circle will share information with these neighbor agents. So let's see what happens in time t2. So we spread the information with the neighbor agents. You can see that all agents change their location. They are moving inside this shared environment, okay? So in the next time, in time 3, the infected agents are now close to other agents. And you see that the white circles are the susceptible agents, and that blue circle is that immune agent. So you can see now will be a contagions and new movements, and so each iteration of the simulation will count with several movement of the agents, maybe contacting, maybe interacting with each other, and sharing information and sharing their status. So synthesis is the agents have parameters, have internal state, have a set of actions or behaviors. The environment is the set of shared parameters among all agents, where they live, where they interact. And the agent-based simulation, it's a population of agents living inside an environment and an execution loop. What is this execution loop? So this is the macro algorithm of the agent-based simulation. We initialize the environment given the parameters. We initialize the population given the parameters, and we have a set of iterations, T iterations, and in each iteration, each agent of the population executes a set of actions inside, given the environment and given the set of parameters, okay? So we update the internal state of the agent after this execution, after executing these actions. After I update the state of all agents, I can generate the statistics of the simulation. Given the population, or the population is the internal state of this simulation, the environment, and the set of the parameters. Finally, I return the statistics, the result variables, okay? The problems with agent-based simulations, it's basically because it is computationally expensive. You can see that we have some inner loops, at least 3 loops, and this, depending on what you do inside these actions, this can be very expanding. And obviously the size of the population, the number of loops, so this is computationally expensive. But there are scalability solutions. It can be scaled vertically by parallelization or horizontally by distribution. Okay, these are some solutions for this high computational cost of the agent-based simulation. Well, our proposal is the COVID-19 agent-based simulation modeling. Our goal is to predict the impact of the social interventions in the epidemic evolution and the economic growth, okay? We restrict the scope of the simulation, but we, in the near future, introduce more variables, more aspects in the simulation and make it be more holistic as possible. You can access the package COVID ABS in this address. You can see bit.ly/COVID_ABS_source, or just take a picture of this QR code. Okay. Our library is open source. It is written in Python using basic Python libraries as NumPy, Pandas, and Matplotlib. Okay, so there's no many dependencies when installing COVID ABS. This library was proudly developed in Brazil, in my research group, SIDIC, and also in the MINDS research group. The SIDIC, it's a research group from the Federal Institute of Northern Minas Gerais in Brazil. And the MINDS, it's a laboratory and research group of the Federal University of Minas Gerais, Brazil. Okay? This is a joint project or joint venture between these 2 research groups. So the library is itself very simple. There are mainly three classes: the class agent, the class simulation, and the class multi-population simulation. Okay, I'm not going to dive into the details of the package. I let this for the programmers to read the code and execute the code, improve, etc. Okay, but what was considered during the modeling of the COVID-19? First, we have the simulation parameters, the shared environment. We have the environment space that has a length and a width, and the size of population. These parameters together give a notion of the population density over over on territory. Okay, when modeling, when applying COVID-19 ABS package to model a problem, you have to take in account the spatial distribution of people. Okay, this you can emulate this with the length, the width of the environment space, and the size of the population. Of course, obviously, as much as greater is the size of the population, greater is the computational cost of the simulation. Also, the number of iterations, the time horizon of the simulation. Okay, we consider that each iteration in COVID-19 modeling has the time granularity of 1 day. Okay, each iteration 1 day. Going ahead, we have some constants that were considered during the modeling. Well, these constants came from the literature, okay, from the knowledge bases and data sets available about the COVID-19 on the internet. The main constants are the contagion rate, the severity changes according to the age, the mortality change according to the age, and there are social and demographic distributions like age distribution, okay, and the wealth distribution in economic. So this is a sample of the data. This table comes from an Imperial College paper, research. To say the truth, comes from an Imperial College report, okay? In the very beginning of the pandemic. So maybe these numbers have to be updated. Probably all of these numbers have increased. This is the age distribution. I'm taking United States as a reference, okay? I'm using the beta distribution to simulate the age distribution. You can see that I don't put the sex, the gender, in the modeling of my agents, okay? This will be done as soon as possible too. And finally, the wealth distribution, the famous Lorentz curve. This graph is comparing two wealth distribution curves of China and United States in different times. Okay, so you can see here we have this distribution. It's in deciles, but our simulation used quintiles. Okay, just 5 quintiles in our simulation. So what are these quintiles? We will discuss soon. Inside the parameters, what are the decision variables? Well, the contagion distance. Why the contagion distance is a decision variable and not a constant? Because the contagion distance can be limited by using masks. and other equipment. Okay, so the contagion distance is not a fixed value. It can be changed. The mobility of the agents is related with the social isolation. Okay, as soon as decrease the mobility, we put the people in quarantine or let the people freely to go and go back. So we have the critical limit. This critical limit is the capacity of the health system. Okay, this capacity is measured by the percent of the population. Okay, this is a decision variable because we can expand the hospital facilities and increase the critical limit. Also, the income and expenses, the daily income and the daily expenses for all agents are decision variables because they are not constant first, and they can be changed using subsidies and tax exemptions. So here is all the attributes of the agent. We have the status, and the general status can have one of these four values: susceptible, infected, recovered, or immune. And that we have a substatus for the infection, is the infection status. The infected person can be asymptomatic, hospitalization, or severe. We count the number of days of infection. We have the age, the position inside the shared environment, the social strata, that one of the key tools of the wealth distribution, the weekly incomes, and the weekly expenses. Okay. So what are the agent actions? First, the movement. So the mobility is the range of the degree of freedom the agent has to move inside the shared environment. So we sample randomly values for its position, horizontal and vertical position, and we account this delta m. This delta m is the total movement of the agent. Okay. And it's important to note that for hospitalization in severe cases, the movement of the agent is equal to 0. For obviously, it will be inside the hospital. Okay. The contact with other agents is when the amount of movement, or the different amount of movement, is close enough or lesser than the contagion distance of other agent. Finally, the most challenging modeling is the economical modeling. Because modeling the infection was already done, but modeling the economical effect, it's really challenging, and a point that still causes a lot of discussion, the way we put the economical modeling here, because it's all about the mobility of the agents. What is delta M represents? Represents the capacity, the capability of the work of an agent. As much as it's move, much it is capable to earn money. Okay, so if the agent become quiet, it will not earn money. What this means? This means that the mobility is responsible to making circulate the money, making circulate the consumption goods, but unfortunately, it also makes the virus circulate. And this question of the mobility is it's what scares all the businessmen, okay? Because the quarantine, in these terms, it means big losses. So this is the main cycle of an agent. First, we're going to start here at the left. We ask, the agent is alive? Yes. So we're going to randomly move inside the environment. Then I will update its internal state. Here I'm checking if the agent have had contact with other agents and a lot of other stuff. Then I will check if the agent is an adult. Okay, if it is an adult person, so I will update the wealth, considering its expenses and its incomes, right? Or if it's not an adult, I come back to the initial cycle. So I will run this cycle until during the update of its internal state, unfortunately, that agent dies. So from this moment to on, we do nothing, okay? How the internal states, this is the state diagram of the internal state of the agent. You can see that the arrows show the status changes, and these changes, these events occur according to some probabilities. Okay, in the case of infection, it occurs if the event contact occur. Okay, if the event contact between two agents was triggered, so the infection may occur. Okay, once the agent is infected, it can be asymptomatic. They need hospitalization, get severe cases, and go to the intensive units, or from that can die. After the count of time, this infected status can be also recovered. So we have the recover event. It's a question of time. The death is a question of probabilities, and the get worse event it's also a question of probabilities. And the infection or no infection is a question of the triggered event contact. Okay, so what are our response variables? The percent of susceptible, the percent of infected people, inside the infected people, the percent of asymptomatic, the percent of, it's missing, of hospitalization cases, the percent of severe cases, the percent of recovered immune, the percent of deaths. I forgot to say that the new evidence shows that after recovered, the people may not be completely immune. So people can get the disease again. So we have to update also this state diagram and our model to include this case. If the people can be infected again and again, this changes everything in the modeling. Okay, the previous speaker, the Robin, if I'm not wrong, discussed this very well. So this percent of recovered immune can be severely affected by this change, and the percent of deaths. For the economical side, we have the percent of total wealth shared by each social stratum. So we have the quintiles, 5 quintiles. The lower quintile is the most poor. The second quintile is the poor. The middle quintile is the working class. The upper quintile is the rich. And finally, the most rich, the 25% of the population with more money. Let's see now some initial results. You can also check the source code of these experiments, okay? Then you can play this. This code can be executed online using Google Colab, and you can play with the parameters, implement your own experiments. Be free to do this, okay? So our general simulation parameters start with an environment with 100 by 100 dimensions, 80 agents, 1% of the initial population of infected person, and 1% of the initial population of immune. We have 1 as contagion distance and a contagion rate of 0.9, okay? The critical limit, or the percent of the population that the healthcare system can afford, is 10%. This is a little bit unrealistic. In the real world, this percentage is much lesser than that. So the first scenario is, what will happen if we do nothing? We start with the mobility of the agents of 5 units by, on the average, 5 units by iteration. So you can see the quick spreading of the coronavirus, and we have a point where the number of hospitalization crosses the critical line, and as the number of the hospitalizations cross the critical line, the number of deaths explodes. This is a tragical scenario, okay? But look for the economic side. The economy never stopped to grow. It's hard to say for some people that preserve lives is much more important. To save lives, it's much more important than to have losses in the economy. Okay, but the economical impact was the major guide for many politicians. Okay, they completely forgot the number of the deaths, the critical limit of their healthcare system, and the tragedy occurs. So after executing this simulation 50 times, we have the average results for the scenario. So this scenario, this simulation is compatible with the results of the susceptible infected recovered model. Okay, so we have a second scenario. It's a little bit utopian. In this scenario, we can quickly detect infected people and put these people in quarantine. So we have extremely fast tests for the COVID-19, and we test everybody and put just that people on the quarantine. We know that this is an utopian scenario, but what would happen? Look, the spreading of the coronavirus will be controlled, and there will be very few deaths. But the problem is that this ultra fast ultra precise and ultra cheap test does not exist, right? So this is an utopian scenario. Let's move on. The third scenario is the lockdown, or to restrict the mobility for everybody. So the mobility of all agents was set to 1. Okay? Basically, this means that they will stay at home. Look, the agents are almost stopped. And we are basically, there's no infection. But look to the economical side. This is the nightmare for the businessman. And this make so many governments to make some absurd policies. Okay, because they don't want to break the economy, but this is the average scenario for 50 executions of this scenario. Okay, you can see that it's a very good result on average contagion evolution, but it's a tragedy on average economical impact. So we tested also the conditional lockdown. Look, for example, when the percent of infected people increase over 10%, then we put the people on quarantine. Then when the number of infected people decrease below 5%, we release, let the infected people in quarantine and release the other people. So we have, it's a good scenario. You can see a peak of infection, but this peak is quickly controlled. Then the people is released. Then there's another peak. So, but the most important is that we could flatten the curve. You can see that the curve of infection don't cross the critical line. The critical line is that dashed line, okay? So if the number of hospitalization and severe cases stay below the critical line, we flatten the curve. So look to the economical side, we can see that we have some losses, but the overall scenario, the economy did not stop to grow. This is the average scenario for 50 executions. Okay, we can see 2 waves of infection, but the number of hospitalization and death are over acceptable numbers. We have also tested the scenario when controlled populations get in touch with non-controlled without quarantine and a population with quarantine, and these populations have some kind of overlapping. This overlapping occurs in the center of the simulation environment, you can see. So there's few contagions from the controlled population, but this controlled population quickly can control these infections. You can see the below population, the number of deaths, and the upper population, there's no one death. So this is a good scenario, what can happen if 2 populations with different policies get in touch, okay? This is a confusing, these mean scenarios are confusing because we are mixing the statistics of the 2 populations. It's hard to understand. Well, the president of Brazil suggested scenario of vertical isolation. What he meant by vertical isolation? We pick the young people and the elderly and put in quarantine and let the working people freely. So these are the different parameters for each one of these agents. Look, it simply does not work. Look, the hospitalization curve touches the critical limit, and the number of deaths will happen as nothing was done. So vertical isolation does not work, at least in our simulations. Okay? This is the average scenario. The average scenario of this conditional lockdown, it's very similar to do nothing. Okay? What?
No, I think there was just some interference, no worries.
Okay. So I have a seventh scenario that is masks for all. That's what I let the people to move freely, okay? I don't restrict the mobility of the agents, but I can reduce the contagion distance by half using masks or other equipment. There's new literature about this, and this literature offers evidence that masks and other equipments are very effective to reduce the contagion distance. So simulating this, the people are moving around, but they're not being infected. Too few people are being infected. So we flatten the curve. We flatten the infection curve and the hospitalization curve. So this is a very good scenario. And the economics, the economics behave very well. So this is a kind of utopian scenario too, because the reality is not that good as we can think. Okay, we cannot reduce the contagion by the half, but it's reduced a lot. Okay, this is the average scenario for several executions. Okay, guys, you may know that quote that says that all models are wrong, but some models are useful. Okay, the COVID ABS showed to be very consistent with the data. Okay, with the epidemic data, but we have problems with the economical data. We don't have enough data. As soon as this data become to be more strong, we're going to update our economical model. But there's a certain similarity between the economical results we observed in these simulations and the statistics and the real statistics of the economy of several countries, including Brazil and the United States. Now we need to go in further. Well, now we change our goal. Our previous goal were to forecast. Okay, now we want to prescribe social interventions that control the epidemic evolution and that minimize the economic impact. How are we going to do this? So now we need to get a broader view of the problem, to put the decision makers, the public rulers, to put the general public, to introduce the optimization to introduce the decision making and to help the public agents to fight the pandemics. So I will explain all of these boxes again. Next step, in this moment, we are in our labs on CDIC and Minds lab, working to improve the COVID ABS library. To improve in what? We want to know what the rulers want, what results they want to achieve, what this means, what the response variables to include, what they want to rule, what the decision variables to include. And we need to research how these response variables and decision cause effect mechanics. So let's start. The second step after improving the simulation framework is the optimization. So the question we want to answer here is, what are the values of theta of the parameters that produce the best values of R, the result variables? So our model now behaves as the objective function for an optimization process. It's important to note that the parameters have restrictions or the range of feasible values. So this capital theta is the range of the feasible values for each parameter, okay? So this is our optimization problem. We have a set of response variables. Each one of these response variables is an objective in our optimization. These response variables are the summary response variables of the simulation, and these parameters are subjected to these restrictions. So I'm going to move a little bit faster because my time is ending. So what the optimization going to provide for us? The set of interventions that the ruler needs, okay? We can represent these solutions or these interventions are vector or production rules. For example, a vector representation is the set of values for each parameter. So we are assuming that these parameters won't change during the simulation, but we can also represent as production rules, and I put certain values on the parameters according to certain values of the response variables. Okay, we can make this problem as a single objective problem. We just to create an objective function that is a weighted sum of the response variables. Okay, each objective have its own weight that measure its importance, but how the ruler is going to choose these weights? This is the main problem. Okay, probably this will be a multi-objective optimization problem, where each response variable will be an unique objective. Okay, the result will be a set of candidate solutions. This is what we know by Pareto frontier. Every solution is optimal and non-dominated. So every solution in this set of solutions, none of them is better than the others. Okay. There's a set of tools to perform these optimization tasks. Probably we have to use gradient-free and black box optimization tools as evolutionary computing and meteoritics and Bayesian optimization. I'm not concerned with this because our team of optimization specialists like Frederico Gadelha Guimarães and our very, very specialist in optimizations, they're going to tackle this modeling, okay? The third step after the optimization is the time to make the multi-criteria decision making. What is this? The problem is generally there are more than one decision making, or the rulers or the managers, and each one of them has different values, priorities, and opinions. And commonly these priorities are conflicting. So how to find a consensus? So the multi-criteria decision-making in groups ask for each decision maker to declare its preferences for each one of these response variables. We average this preference and find the solution that best fit the averaged preferences. Okay, we call this the compromise solution. This that solution that satisfies the parties involved and with mutual understanding. It's the consensus solution. Okay, so I have the set of candidate solutions generated by optimization process. I have the group of decision makers, and have these decision makers will create the set of preference of priorities. Okay, they will input this preference for each one of these response variables. Finally, the multi-criteria decision-making method average the preferences, multiply, it's not a multiplication, but let's go. Multiply this averaged preference by the candidate solutions, and after this operation, we have the solution ranks. We sort the solution ranks, and the solution with the highest rank will be the compromise solution. So we have a lot of options here. We have a specialist in multi-criteria decision maker, is the Marcos Antonio Alves, our specialist in multi-criteria decision making. And finally, this is the broad scenario for what we want to do. We want to employ the simulation to help public managers, to help the rulers, to improve the interventions and to improve their decisions based on data, based on simulations, based on the best values for each one of the decision variables. Okay. Concluding, a little bit late. It's possible that agent-based simulation is a feasible solution for COVID-19. We developed the COVID ABS package that is free, open source. We still having modeling changes because the pandemic is changing, but we already have some initial results. Finally, the next steps are to put COVID ABS in a broader framework that includes optimization and decision making. Okay, so let's get in touch. Please, all contributions and questions are always welcome. You can send it for us. We are continuously working on this framework. And finally, thanks. Thank you for the invite. Thank you for my my fellows in the CDIC research group, in Minds research group, and thank you also for the invite to this simulation. To this simulation, not to this talk. Thank you. Let me. I'm have difficulty to.
Yeah. Thanks. Oh, we've lost. Oh no. Yeah. Thanks, Petronio, for a fantastic and detailed walkthrough of your simulations. I think we don't have too much time for questions now, since you did such a thorough job here, but we may be able to do maybe one or two quick questions if you see anything good on there, Marcello.
Yeah, there has been some really good questions coming through throughout the whole talk of Petronio, which means that the audience had found it really interesting. I'm just going to read some of those. Would it be useful to have a slide comparing all scenario results overlapping or side by side? Which scenario was best in the end, mask or control population?
Just a second. I want to stop the sharing, but I don't.
No, now we can see you. Now we don't. You're not sharing anymore, so now it's fine.
Thank you. Okay. Well, I do not make comparisons between the scenarios. Okay, I'm trying to do not make value judgments. Just one. The life has not price. Life is untouchable. So the economical aspect of all simulations are a guide for the public power to soften the social effects. But obviously, if we compare the scenarios, you can see that the total quarantine is the better scenario for the life. Is the scenario that has the optimal number of deaths. That's the great response, the major response variable we have to pay attention. But once we cannot control everything, I think that there will be an intermediate scenario that's an intermediate conditional scenario that is to be discovered by the optimization process, okay? That can handle the health and the wealth effect as well.
Okay, so we have some more questions. Would you consider restricting mobility in the agent environment to and from certain location nodes, such as home, offices, schools, shops, with transportation links between them?
Not yet, but we are looking to implement this soon, because this is another level of the agent-based simulation. One thing I have in mind is the shared environment, instead of being a squared place, to be a graph where the edges represents the streets and the avenues, and the vertices, the vertex represent the spots, the places, the houses, the facilities. Okay, this will become more accurate, the social reality for the simulation. But for this moment, we did not implement this yet. Okay.
Yeah, of course you can layer this on top of a whole GIS system and realistic maps and so forth. And we've been playing with a little bit of that. Eva has done things like that. So I think that, the very simple models are valuable to show the qualitative nature of what phenomena we're looking at, which I think your models, Petronio, have done outstandingly. And then when you want to guide highly specific policy decisions in specific places, then you need to add in maps, and you need to add in detailed information about different populations and so forth. So you need both. I mean, you can't build the complex model until you know how the simple model works.